friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll explain parametric study and optimization of an exhaust gas system of a petrol engine, and this will be done using SolidWorks flow simulation. Analysis part of this one has already been explained in another video. Today in this video I'll explain mainly on the parametric study and its optimization. You already know this system is consisting of three different parts. First part is known as catalytic converter. Second one is consisting of three different parts. It is having perforated pipes, then muffler and resonator. And the third part is also called resonator. In this case, our goal will be to have the temperature at the exit end, and that we have to optimize with respect to some input variables. So without wasting time, we can start this analysis. It will be start with flow simulation, and that flow simulation environment will be created with the wizard itself. So we're starting with wizard, and default name of this project we're keeping as project 7. Next, the system we are considering as SI system, and the temperature will be considering as degrees Celsius. Next, it will be an internal analysis, and we are considering heat conduction in solids. Next, gases we are considering air, carbon dioxide, water vapor and nitrogen. So it will be air, carbon dioxide, water vapor and nitrogen will be there. So we have taken air, carbon dioxide, water vapor and nitrogen. Next, so the material for this system, it will be alloy steels, and we are considering stainless steel 321. Next, the default outer wall thermal conditions and roughness we are considering, and actual values will be provided during actual applications of boundary conditions. Next, thermodynamic parameters. So the pressure will be 101325 Pascal, and temperature will be definitely 20 degrees centigrade, and definitely the solid temperatures will be 20 degrees centigrade again. When this is very important is concentration, right? So as we're considering petrol engine, it will be having carbon dioxide, water vapor and air. So percentage of carbon dioxide will be 15%, water vapor will be 15%, nitrogen 70%. And as we are considering air from outside, so initially concentration of air will be 0%. So you can see that percentage of carbon dioxide is 15%, percentage of air will be 15% again, and nitrogen will be 70%. Finish. This is the computational domain. We can edit this part to ascertain that all the parts of this model should be inside this domain. Let's edit this part to make it sure that all the parts of this model is inside this domain. So our computational domain is ready. I'm going to check. Now we can hide this part for our analysis. Computational domain, let's hide it. For now the model is ready for applying boundary conditions, and we have already told that for better application of boundary conditions, it is always suggested to have a segmented view of this model. So we can cut this model from the front end. You can check, we have cut it. Now we have to apply the boundary conditions. Boundary conditions, insert boundary condition. We are considering inlet mass flow rate of exhaust gas as 0.02 kg per second. Thermodynamic parameters, we are considering 101325 Pascal and temperature to be 700 degrees centigrade. And substance concentration is very important. We told already that carbon dioxide will be 15%, water vapor will be 15%, air will be 0 and it will be provided from outside. 0% air will be there, and nitrogen will be 70%. Let's check it again. Carbon dioxide will be 15%, water vapor 15%, nitrogen 70%, and air will be 0% at the beginning. Now the location of this exhaust gas entry will be selected. You can select it by checking this one. This is the location of inlet of exhaust gases. I'm going to check it's done. Now we have to apply the second one, that is air to be applied at a specific location. Again, for that one we can cut it across a specific location. We can make it bigger for proper selection of this location. Green check. At this location we have to apply air particles at a specific rate. So boundary conditions, insert boundary condition, and we are planning to have air at a rate of 0.01 kg per second. Thermodynamic parameters will be 20 degrees centigrade and 101325 Pascal. And substance concentration is very important here itself. Carbon dioxide will be 0%, air will be 100%, so its concentration will be 1, water vapor 0, and nitrogen also will be 0%. You have to select that location, select it, green check, it is applied. So 2 boundary conditions have been applied. Now we can see the other one, that means we can apply on the second chamber. That means we have to apply porous material at the second chamber. Is coming from conditions porous material predefined, it will be isotropic, that means throughout all directions its porosity will be same. So select that location, and here in this case we are considering porosity to be 50%, that means 50% of volume flow rate will be reduced. At the same time pressure also will be reduced. Green check, porosity is applied. Third boundary condition we have applied. Now the fourth one, that means atmospheric pressure at the excitant to be applied. So we can cut it again across the specific location. Green check. You can make it a little bigger for proper selection. Now boundary conditions, insert boundary condition, and you want to apply atmospheric pressure or environmental pressure at the excitant. Green check. Fourth boundary condition is also applied. Now we can select the complete view of this model, and finally the walls to be selected. We want walls to be transferring heat at a rate of 90 watt per meter square degree Kelvin by convection. So last boundary conditions, inside boundary condition, it will be from the outer walls, and convective heat transfer coefficient will be 90 watt per meter square degree Kelvin from the walls. So we can select the walls from the geometry itself. So all the model is selected. We have applied the last boundary conditions, that is wall conditions. Wall will transfer heat at a rate of 90 watt per meter square degree Kelvin by convection. All the boundary conditions have been applied. Now we can select some goals. Our aim will be to have the exhaust gas temperature at the exit location, and that to be optimized with respect to some input variables, right? So we have to select the goals. Again, we can cut this object along some specific location. So goals, insert surface goals. We want to have average temperature of fluid at the exit location. Selected at phase 1, green check. So the boundary condition is, so goal is also defined. Now we can run this simulation. Let's run it. The Solo window has started its iterations. It is preparing the model right now. Mesh capturing is going on. Mesh generation is finished already. It is preparing for calculations right now. You can see that exit end temperature is 19.99 degrees centigrade. You can see from the graph itself and from this sketch, you can see the results from the sketch. Settings, we want to see temperature of fluid at the exit location. You can see from the graph also. See, maximum temperature is 19.99 degrees centigrade approximately. It has come down to 15 degrees centigrade, then it has started increasing. We can view these things from the original drawing also. Let us increase the image attribute to be 1000 by 1000 to have a better view of this drawing. You can see at the entry level temperature is 700 degrees centigrade, and as it is approaching towards the exit end, its temperature is reducing also. At the exit end, still the temperature is 14.54 degrees centigrade at this location where the color is completely blue. Iterations are going on. You can see the change of color through this iterations timing. At different times, color is changing to show that temperature gradient across this passage of this system. Still at the entry point, temperature is very high, that is in the range of 700 degrees centigrade, and you can see that at the location where we have provided these perforations, that means we have provided this specific material known as porosity, temperature is very less. Because of porosity only, volume flow rate has been reduced, by the same time pressure and temperature also reduced. Still now 68 numbers of iterations are complete. Okay, again you can see these results from the graph. Let's see from the graph. It is showing that initial temperature it was less. As time is approaching, it is going high. Now it is in the range of 215 degrees centigrade. Inlet temperature of exhaust gas was 700 degrees centigrade, and exit temperature at this moment is 277 degrees centigrade. 110 numbers of iterations are complete. Let the iterations move on. Whenever it is finished, we will see the results and go for analysis. The solver has finished his calculations or iterations. You can see at the end of 223 numbers of iterations, the maximum temperature at the exit end is 363.88 degrees centigrade. So maximum temperature is approximately 364 degrees centigrade. Okay, you can see this from the result also. Let's see the result. Cut plot and other things we are not bothered about because we have already seen these things in our previous video. When you check the exhaust gas temperature from the goals plots, insert goal plot, and when you see the surface goal at the exit location, you can see that exit gas temperature, minimum temperature is 359 degrees centigrade, maximum is 363.89 degrees centigrade, and average is 361.28 degrees centigrade at the exit location, right? Initial temperature of exhaust gas was 700 degrees centigrade, and by the application of these perforated tubes, or you can say the porous material, it has been reduced by almost 50%. From 700 degree to 359 degrees centigrade at the exit location, right? Now we can go for further reduction of temperature by optimization. For optimization, you have to depend on cooling, and here in this case we are providing cooling by supplying air from this location. We provided air at a rate of 0.01 kg per second. If we increase that mass flow rate of air, better cooling will be provided. So in this optimization or parametric study, we will vary different flow rates of this air and see at what rate what will be the temperature of the exit location. We are planning to have a temperature of the exit location as 200 degrees centigrade, and we don't know at what mass rate of air the temperature of exit location will be 200 degrees centigrade. That we'll find out. Okay, so initially we're going for this parametric study to have different ranges of temperature at specific ranges of mass flow rate. From these values we will go for optimization, right? So we're starting for parametric study from here itself. Solve new parametric study, and we're going for design of experiments and optimization. That means with specific values of input variable, that means the mass flow rate of air, we'll try to have different temperatures at the exit location. Okay, so the input variable to be defined from here, and it will come from definitely boundary conditions. Inlet inlet mass flow rate 1 was for exhaust gas and inlet mass flow rate 2 was for air. So we have to select this second one, mass flow rate of air. Green check. Initial value of this mass flow rate of air was 0.01 kg per second. Now we have to increase that rate to have a reduction in temperature at the exit location. So we will specify this range from 0.02 kg per second to 0.05 kg per second. Then check, and we have to specify the goal. We have only one goal that to be defined, that is exit temperature of fluid. Let's see the scenarios. With the specific input variable range, we are having 5 numbers of experience. Let's create that scenarios. This scenario is automatically done. We can vary these things as per our requirement. Let's run this one and see at this specific mass flow rates what are the different temperatures at the exit location. So run it. Solve window has already started iterations. You can see the first experiment has already started. It will take some time to get all the experiments to be completed. Whenever it is finished, we'll see the results and go for analysis. Okay, all the iterations have been finished. You can see here right now, like from experiment number 1 at mass flow rate 0.0425 kg per second, we got the temperature as 185.13 degrees centigrade, and at 0.0275 kg per second mass flow rate, we got the temperature as 245.96 degrees centigrade. When the mass flow rate is 0.05, it is the exit gas temperature is 162.02 degrees centigrade. At 0.035 kg per second mass flow rate, the temperature is 207.38 degrees centigrade. And finally, at 0.02 kg per second mass flow rate, the temperature is 286.528 degrees centigrade. From these experimental results, it is clear that when the mass flow rate of air is very high, exit temperature of exhaust gas is less. We have planned to get the exit temperature to be 200 degrees centigrade. For that, we have to specify the range for final optimization. From this data, we can see that the temperature of exhaust gas should be 200 degrees centigrade with a specific mass flow rate of 0.035 to 0.04 kg per second. That means from this design, experimentation and optimization, we got some idea that what is the specific range required to get the optimum result, right? So next one, we have to go for optimization with the specific range from 0.035 to 0.04 kg per second mass flow rate of air. Finally, we'll go for goal optimization. Again, in this case, we have to define the input variable. Like the previous case, the input variable will be mass flow rate of air, and we have to specify the range. It will be 0.035 to 0.04 kg per second. Select the goal criteria, and criteria is dependent on goals. We have only one goal to be finalized, that is average temperature of fluid to be 200 degrees centigrade. Green check, and target value we are fixing as 200 degrees centigrade. We want to achieve this temperature with a variation of plus minus 0.5 degrees centigrade. Green check. Let's see the scenarios. We have maximum 128 numbers of calculations. Let's run it. So from this final optimization, we want to have the temperature of exit gas to be 200 degrees centigrade, and for that we have specified a range of air from 0.035 to 0.04 kg per second. The iterations have already been started. First iteration has started with the maximum value of mass flow rate. First of all, with the maximum mass flow rate, it will try to find out the temperature at the exit location. Next one, it will try with the minimum one. In this way, it will try to minimize the gap and try to find the optimum result. The iterations are going on. Whenever it is finished, we will see the results and explain it for further clarifications. Iterations have been finished. We can see the solution is converged within our specified range of mass flow rate. We got our optimum temperature as 200 degrees centigrade. First iterations at a mass flow rate of 0.04 kg per second, we got the temperature as 192.77 degrees centigrade. We got a variation of minus 7.2 degrees centigrade. In the second iteration, when the mass flow rate is 0.035 kg per second, the temperature at the exit end is 208.73 degrees centigrade. In this case also we got a variation of plus 8.73 degrees centigrade. And in the third iteration, at a mass flow rate of 0.037 kg per second, we got the exit temperature as 200.03 degrees centigrade. In this case, we got a variation of 0.03 degrees centigrade. So this is our optimum data, right? So our result is optimized. When the mass flow rate of air is 0.037 kg per second, the temperature at the exit level will be 200 degrees centigrade. This is all about our today's parametric study and optimization of exhaust gas system using porous medium. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.